All right, welcome to Module 7. This is Chapter 13, Highway Curves, beginning on page 365 of your book. And I just wanted to point out that probably scared you a little bit when I said we were going to, in the intro video, we're ready to start Chapter 12. That was last week in the machine control. So this week we are looking at curves. There is many types of curves, but every curve that we talk about is necessary for a street. Um, Basically, I mean, there is one particular curve that's used for streets, superhighways maybe, and we'll talk about that toward the end of this lecture. But it's also mainly was used for railroads, and we're not going to have to worry about computing that or doing anything with it. So what we're going to look at though is circular curves as well as vertical curves. And the reason for a curve is so that you have smooth transitions. This is important to know. You need a smooth transition from one spot to another where you would have, one tangent, they're called, one straight section of the road to another. If you didn't have curves everywhere, everybody would have to come to a stop and make a 90-degree turn, or roughly a 90-degree turn every time they wanted to go somewhere. So curves allows for to have a smooth transition from one straight section to another. And with that being said, I'm going to go ahead and share my screen, and we'll look at the slideshow here for the moment. Let me pull this up. Bear with me, we're hanging in there. All right, screen share we go. And this is the one we want, and we are now sharing. All right, so chapter 13 here, highway curves. I'm going to show you the geometry of a curve, but you're not going to have to deal with this very much, but I'm going to teach you some of the geometry behind the curve. And the purpose of that is so that you understand why we need to have it. And I'm going to show you some of the interesting things about a curve. We're not going to be doing any math. We're not going to have to worry about much else other than what these terms are and how they work together. So you have a curve. This is a typical diagram of a curve. Surveyors see this particular view often. So what we have here is we have a tangent section coming into to another tangent section. Without a curve, we'd have to have a stop sign up here at this point of intersection, or point of, some people call it tangent, but most people will call it the point of intersection, which is right here. The curve is always a 90-degree angle off of each tangent line for the same exact distance to a radius point. This is important to know, in that you're starting to see triangles happen. We've got a triangle here, some direction. We've got one happening here, but radius of an arc, and this is a circle. If it wasn't the same radius at the beginning and the end, we'd have something other than an arc. It'd be an ellipsoid or something. And we're going to talk about one toward the end of the lecture that is not the same as an offset in the radius. So you have components of the curve to think about. We have a beginning point. Sometimes this is called the PC, point of curvature. We have an ending point, and most people will call this the PT, point of tangency. Out here is your point of intersection. Here is your radius point, and keep in mind this O is theta. You will see that from time to time, and if you're just dealing with math, surveyors don't usually think about it as theta, but you can think about it that if you wanted to as far as math goes, because it's how you solve for this arc right here. So we have a long chord. This is also something that pops up and is kind of important to surveyors. We want to know this distance from the beginning of the curve to the end of the curve right here. And we also want to know this angle. This angle down here is called your delta angle, which is the same as this up here. That delta angle is how we figure curves out and how we know how to stake them. So each one of these components is important, and there's math behind all of it. And we're not going to go worrying about the math right now, and you're not going to have to solve any curves. But the issues that you need to take a peek at again here is that this is called a delta. These are called tangents from here to from the beginning of the curve to the PI, the end of the curve to the PI. These two distances are the exact same. Radiuses are the exact same. The delta is the same as this angle right here. And half the delta is also, it puts you right in the middle of the PI. So half this angle is going to exactly be the point of intersection. And sometimes people want to know what this distance is from here to here, and it's called a middle ordinate. But it's not too important and not used too often. That's pretty much the basics of a curve. So you have your tangent coming in, your tangent going out, and you see here, you can study this, but to get the relationship, I often still am doing curves with a calculator and a little bit of trigonometry and solving for this arc length and using this delta. And if you remember anything from math, S equals R theta, where theta was in radians. So I would convert this angle to radians, multiply by my radius, and it will give me S, the arc length. Surveyors always use L for an arc length. Mathematicians use S as in for length. So I'm going to skip through. There's not a lot of things that I'm going to show you other than the first two slides, and then we're going to talk a little theory. Here you'll notice though that we're dealing with an arc, and here this circumference, the entire circumference is 2 pi r, and that's where you start to get broken down into your radians. 2 pi r, or 2 pi, is the number of radians in a circle, I believe. But it's, yeah, I think, yes, that's right. So 2 pi is the number of radians in a circle, 2 times pi. But again, you don't need to worry too much about all of that. And I'm certainly not going to ask you anything this about the stationings and how everything fits. What I do want to get to, these are deflection angles. Now, when I first started surveying, 30 some years ago, this is how we had to stake curves, with all these different angles that we had to figure out to deflect ourselves around the curve. You don't have to do that anymore because the data collectors handle everything. Your geometry will be in the data collector. The coordinates, the X, Y, and Z values of your beginning points and your end point of the curve, as well as any point on this curve, can all be figured in a data collector with the coordinates being assigned to them, and then your data collector will tell you what angles and distances to turn to stake out the curve. So you don't need to do this anymore, and that's why I'm telling you that the book has some archaic information with regards to how to stake things out. This right here, this was one of the more difficult moves, when you would have to set up on this station and then get yourself oriented again and stake out the rest of it. But now, like I said, with coordinates, everything being X's and Y's in the data collector, there's no issues whatsoever of having to stake out a curve. I want to come back to this. I think I want to come back to this. Let's see. Yes, we don't want any of that. I will come back to that cross section. Let me go back here. All right. Here we're starting to see a different type of curve, and this is what I want to talk to you about. This is a compound curve. We're also going to talk about reverse curves in a minute. So the other one is basically just a general circular curve. Here we have a situation where we have a tangent line coming in, we have a curve, then we have another curve, and a tangent line going out. So what we have is we have this spot right here, this point of compound curvature, PCC. And the reason it's a compound curve is because we don't have a tangent, we have another curve with a different radius. And when you use that, there's ways to figure it out. And this is a tough thing to do, but it's when you just have like an odd situation with a road where you have to come in with one radius and sort of tighten things up in the curve or expand them and get out to the other radius. It's not something that is done very often, and county jurisdictions frown upon surveyors and engineers laying roads out with compound curves in them. They really don't like them, but it happens sometimes. One place it'll happen is, well, I won't worry about that. Don't worry about that. So, but you can look at this and you can see the geometry of it. The one thing I want you to know about a compound curve is this radius line right here from where the PCC is, this point of compound curvature, which if it wasn't a curve, there would be a tangent line coming out here, and this would be the end of the curve. It's a straight line from this point through both radius points. It has to be a perfectly straight line between all 3 points, or you have something that's not a compound curve. You have something geometrically wrong. So that's what you need to know about a compound curve, that the radius points all line up. Radius point, point of compound curvature, a straight line, 180 degrees from there to there, and it has to work that way because of the geometry. I'm still going to go back to that cross section. This is a situation you see more often. You've probably seen things like this on an old country road. You know, literally the slippery when wet sign on the highway. You have a curve in one direction followed by a curve in another direction. We have a tangent coming in, a tangent going out, and the road has to curve once, get to a spot, curve back again, and then we can head on in our direction. What you need to know on this one, and you can again look at everything with geometry, but instead of having a point of compound curvature, we have a point of reverse curvature. The key to this one is that this radius point right here, through the point of reverse curvature, and this radius right here is also a straight line. Right through them, 180 degrees from right through there. It has to be a straight line. So that's something you're going to want to know about, something I'm going to ask you about with regards to how curves work. And again, could you imagine like trying to maneuver this without a curve? You have to get to a point here, you have to stop, you have to come down this way, stop, and then go this way. And then now you can just make a nice smooth transition from one curve into the next and out the other tangent line. So curves are very important. I've just shown you 3 different types of curves. I'm going to show you a 4th one up here, coming up here in a minute. This is another type of curve that you'll need to use. This is a vertical curve. Vertical curves are very important on a road. Could you imagine if you were driving on a road and you get up here and you got to come to the top of the hill and stop? Because if you go too fast, the bottom of your car is going to hit the point in the road, because the road comes up and drops off straight down there. You'd have to be very careful. You probably, a lot of times, if it's just too steep, the bottom of your car is going to hit the pavement. It just makes no sense to have something like that. A lot of times you will encounter a faulty entrance into a parking lot where it dips down, where this particular it's reversed. We're looking at a dip in the road instead of a hill like this, where you come through and your bottom of your bumper or something like that will hit and it's because the curve is not correct, coming off the pavement and into the parking lot. So with regards to these, they're called vertical curves. You have a beginning of the vertical curve and you have an end of the vertical curve. You have two different grades, a grade 1 coming in and a grade 2 going out. You solve these with the algebraic difference, but notice the length of the curve. The length of the curve is not actually this right here. The length of the curve is measured from the stations, from the beginning to the end. So that this is all figured a little differently. This math is a little bit different than the math that you use for a horizontal curve. And you'll see this radius does a little bit different thing. It kind of changes a little bit to more. It's sort of slightly changing as you go through it. So this is like I said, this is a vertical curve. The components of a vertical curve, you won't need to worry about the math, but you will need to worry about the purpose of it. This type of vertical curve here is when you get to a low point. You're coming down and you have to climb back up a hill. So that's a sag. These are just different types of, this is a crest curve, just different types of curves. I'm not going to ask you about this, but you can look at it if you want. You can look through the book, but this is how you figure out the elevations of these curves by utilizing this geometry. One of the things that is interesting with the curves like this is you have low points and high points, and you have to figure that out. Do a little math here, but what you're looking for here is that when this grade changes, you can see you're coming back up. You have to know where this low point is, because that's usually where a ditch is going to empty out, or you're going to have some sort of pipe underneath the road. So these are things that surveyors and sometimes construction people might have to figure out. All right, this is the curve that I'm going to tell you about that we don't need to fool with at all, and I'm not going to ask you about it. But it's interesting to know this is a spiral curve. A spiral curve has like this ever-changing radius. And let me come in here and show you. Here, this is the one with the shifting circular curve. So what you end up with is you have this offset. In other words, as a curve comes through, it changes, and this point here, this it's called the tangent start. I think that's what the TS means, but you start in here with this little bit of a radius. Here's like a regular curve, and then you come out with a different radius. These numbers, like this radius from here to here, here to here, are all different. The only thing that's the same is the start of curvature and the stopping of the curvature right here. Spiral start and stops the spiral. These are done, and when we go back, these are be done on superhighways where you need to travel really fast, or trains, because you get the idea a little bit about physics. See how this curve is coming in, it's getting tighter. That centrifugal force will actually keep you on the road, or keep a train on the track as it goes around a curve, because it's pulling it. It's pulling the car or the truck or the train, it's pulling it toward the radius point because this thing is changing. That's the benefit of a spiral curve. you're hardly ever going to see one construction-wise. And if you do, the surveyor is going to figure it all out for you and make your life easier. So you don't have to fool with much of this at all. One of the things that we're going to go back here now and look at, I'm going to look at two more things for this this chapter. I think I skipped it. Where'd it go? I think I'm going too fast. Here. This is what I wanted to show you about road cross sections. We're going to talk a little bit more about this in the chapters to come. But, oh, lost it. What you end up with is a cross section of a road. The book is going to talk about this. I'm going to ask you some questions. It seems like I've brushed through curves, but the purpose of it is that you lay out these cross sections on the road's horizontal and vertical geometry. So as the road was making those curves, like this, as the road makes these curves, or, you know, literally as you're going up over a hill, however it is, you will be applying what's called a cross section, and that is right here. This is called a cross section. You'll see here's your center line of the road. These are your slopes down to each curb and gutter. You'll come up, it says here layout stake. Don't worry about that. You usually would come up and have some kind of sidewalk, and then you know, a slope taking you over to the existing ground and making a nice smooth transition. So what this is showing you is how cross sections are laid out, the fact that they're repetitive, and you have to place this cross section over top the horizontal alignment and the vertical alignment in order to stake a curve. It sounds like a lot going on, but it's not that hard in practice, and the reality again is that your data collector is doing the job for you most of the time. If you're ever interested, here's all the different components of a spiral curve. Again, I will not be asking you about spirals. This right here, and oh, the diagram doesn't do a very good job of telling you what this is, but there is something called a super elevated curve. And the super elevated curve is, let me see, is there another picture that's better? Not really. Nope. A super elevated curve would be such that you would come through like this. You're driving down the highway and you need to make this turn. You would transition from here. In other words, you're driving and this is a crown in the road. And I'll stop my share and I'm going to diagram, show you this with my hands. Stop sharing screen. So as you come down a normal highway, it has a crown. So that one side of the road is sloped and the other side of the road is sloped and the high point is in the middle. As you go around the turn, what tends to happen is this happens. You transition into a banked curve. And let me go back to the screen share. Right here, we're going to share it. So as you come through, you start to tip toward a fully banked curve over here with this transitional section. And by the time you get to here, you're in a fully banked turn. Now, why is that important? Well, earlier today was the NASCAR race at Talladega. If those curves weren't banked, the cars would fly off the track. They could not travel at nearly 200 miles an hour and stay on the track without a banked curve. And that banked curve, again, it goes back to physics and the centrifugal force of going around that bank, pulling you back toward the ground and pulling you around the curve is why we have super elevated curves. You will find super elevated curves anywhere there's a very sharp curve and the designer of the road wants to maintain the speed. One of the places that I remember is on the Beltway. There are many places on the Beltway where we have super elevated curves. As you go around a curve, you'll notice 3 or 4 lanes wide. You'll notice the slow lane, so to speak, will be lower, and you'll see it that the outside lane, the fast lane, will be higher, and that is a banked curve. And you have to transition into that fully elevated banked curve. So on something like this, we have a horizontal curve that we're dealing with. We have a vertical curve that we will be dealing with for the elevations of the road. And then we're going to have this transitional, this fully super elevated curve where the pavement itself is tipping. So we're handling things in 3 dimensions as we stake out a road, all for safety, all to keep the cars on the highway. So I think that that is actually going to do it. There's a lot of information here kind of covered, and I would be available again tomorrow or Monday at 7 o'clock for office hours. Any of you have any questions? I know that's a short notice. I will give a different date for the final. I'm going to have office hours on a Tuesday or a Wednesday so that you have time to look at the material, listen to what I have to say, maybe ask me some questions for clarity's sake, and take the final exam. But this week, Module 7, my office hours will be on Monday. So I know that seems pretty quick, but I want you to understand the theory behind the curves. Know the compound and reverse curves. Know that special relationship between the radius points. And then also understand that the purpose of the curves is to make smooth transitions, whether it be horizontally, vertically, or even the inside the lane of a pavement where it's the lane itself is super elevated. So this is going to wrap up chapter 13. 14 and 15, I'm going to go through them pretty quickly as well. There's a lot of stuff in there that you're not going to be too necessary for you to learn it too much as a construction manager. But I will go ahead and stop the video and we'll come right back here with chapter 14.